Okay, let's start with an example here. I'm going to write down a simple integral. Let's say we're going to integrate x squared with respect to x from, how about if we say 12 to 15? Okay, so suppose you were going to work that out. If you go by the previous lecture about Riemann sums, then you would know that what's happening here is you look at the graph of x squared from 12 to 15, and you do those Riemann sums in here. And it's a lot of work, right? And you do the limit as the width of the rectangles goes to 0, and it's a lot of work, a heck of a lot of work, okay? Or, you know from the lectures before that there's a faster way to do the problem, which is to write down the antiderivative of x squared, and then plug in 15 and 12. And we won't bother working it out, but the point is it would be 1/3 times 15 cubed minus 1/3 times 12 cubed, and then you would get your answer. Okay, so the last thing that we need to do is I need to explain to you why this works. Okay, I need to explain to you why does this equal this? Okay, that's what we're going to do today. And then after that, then we'll just spend the last of the lectures just practicing calculating integrals. Okay? All right, so what we're going to do is we are going to cover something called the fundamental theorem of calculus. Okay? So let me write this down. Let f be a continuous function on some closed interval, let's write from a to b. Okay? And so that was a lowercase f, okay? So here we're going to let capital F be this function. Capital F of x equals the integral of little f from a to x. Okay, now I have used the variable x right there, so I can't put x here and here. I need to use a different variable. So we'll use, let's use t. Okay. All right. Then capital F is differentiable and the derivative of capital F will equal lowercase f. Okay, so let me put it here. In other words, capital F is an antiderivative of little f. Okay, so let me prove this for you. It's not too hard to prove. Okay, takes a little bit of work, but not too bad. All right, so here's what we're going to do. Let's write down what would be capital F prime of x. Okay, what is a derivative? You need to remember that. All right, so you should know what it is. It's the limit as h goes to 0 of capital F of x plus h minus capital F of x over h, correct? That's the definition of a derivative. All right, so what would that look like? Remember, here's what capital F looks like right there. So this would be the integral of little f of t dt from a to x plus h minus the integral of little f of t dt from a to x, and then that is over h. Okay, now look at those two integrals here. Notice they both start at a. Okay, this one ends at x plus h, this one ends at x, and I am subtracting the second one from the first one. So what are we going to get? If you take the integral from a to x plus h, and then you subtract the integral from a to x, you're going to be left with, what will be left over? The integral from x to x plus h. Okay? And this is up to you, but you might like it better. You might think it looks better if we write it like this. Okay, so there we go. I know that capital F prime of x will equal this, if this limit exists. Remember, when something is a limit, then it might exist, it might not exist, because some limits exist and some don't. So what I need to do is I need to show you that limit there, which is highlighted in green, exists. That means capital F has a derivative. And then the second thing I need to show you is that that limit actually equals little f of x, because that's what I'm trying to prove. See that up there? I'm trying to prove that. Okay, so let's do this. Let's just scroll up so that we're only looking at that thing there where we left off. Now, how are we going to show that that limit equals little f of x? Just a second here. Okay, there we go. All right. So I think maybe what we should do is we're looking at the limit as h goes to 0, so that means h might be positive or it might be negative, right? So let's go ahead and split those into two cases. Let's just suppose that h is positive for right now. Okay, let's look at a hypothetical picture here. So suppose we have, here's x, and here's x plus h. And maybe the graph of little f looks, you know, something that maybe. Okay. All right, now we're only looking from x to x plus h. And those are inside of a and b, by the way. So maybe a would have been like right here and b would be right here. Okay? All right, now, one thing we said was that little f is continuous. So the extreme value theorem means that little f has a maximum and a minimum when we look at this range here. Okay, there's a maximum and a minimum. You can tell what they are, can't you? Here's the maximum right there, and here's the minimum right there. Okay, not the minimum of the whole function little f. I'm just talking about just between x and x plus h. And let's even do this here. Let's make it so the minimum's not right on that edge line here. Let me do this. I'll just change the graph a little bit here. Let's do that. So now we have the maximum up here and the minimum down there. Okay? All right. What I want to do is I want to think about this. Don't worry about the 1 over h in front right now. Just worry about that integral right there. What is that integral? Okay, that integral is equal to this area, correct? We know that, right? Okay, now I am going to copy this picture here. It might not come out looking exactly the same, but as long as it's close enough, that's fine. And then I'm going to copy it again. Okay, now, here's what we're going to do. Let's look at the maximum of little f. Remember that blue graph is a graph of little f, okay? Not capital F, little f. So let's look at the maximum of little f between x and x plus h. Let's call that maximum value capital M. Okay? And let's look at this rectangle. What's the area of that rectangle? Well, that's really big. What would be the area of that rectangle? Do you agree that that area would be width times height, right? So h times capital M, right? Okay, let's look at the minimum of little f between x and x plus h. Let's call that lowercase m. And let's look at this rectangle. What would that area be? Well, again, it's width times height, so that would be h times little m, right? Okay, and let's write down what is this area that I shaded in pink, by the way. that area is the integral of little f from x to x plus h. Okay, now think about this for a minute. Just look at the pink areas. The first one is oddly shaped, but the second and the third one are rectangles. Okay. Do you agree that this area right here is definitely between these two? Not just by looking at the picture. I'm not saying, oh, look, the first area is between the second two areas. No, you can give a logical argument why. Because capital M is the maximum of little f between x and x plus h. So the amount of area that is below the line y equals capital M will be more than the amount of area that is below little f. Okay, and on the other hand, lowercase m is the minimum of little f. So the amount of area below lowercase m is going to be less than the amount of area below lowercase f. It's possible, depending upon what f looks like, it's possible that the areas could be equal. If f was actually a horizontal line, then those three pictures we have there would actually be three rectangles that would all be the same size. Okay, but the point I'm trying to make here, and this is what's important. Whoops. Okay, the important summary is this. This amount of area, which is in the first picture, is definitely less than or equal to the amount of area in the second picture, and it is definitely greater than or equal to the amount of area in the third picture. That's the important point. Okay? Now let's look where we left off in our gray writing up above. Look at where we left off right there. Look at this. We were left off trying to figure out the limit as h goes to 0 of 1 over h times that integral. Okay, now down here, I've said that that integral is between h little m and h big M. Okay? Let's do this now. Okay, I'm going to scroll back down here and let's make this a little bit bigger. Okay, let's do this. Let's do the limit as h goes to 0. Or let's actually do this. Okay, sorry, I paused for a minute because I was just thinking for a minute. Let's do this. Let's divide all three sides of that inequality. Let's divide by h. Okay, we'll do that first. So I'm going to divide by h. Then I'll get m, little m. H is positive. Remember, we're doing that case first where h is positive. So the direction of the inequality will not swap. Okay, divide the middle part by h. Okay, and then divide the third part by h. Okay, so there we go. Now let's do the limit as h goes to 0. Okay. Remember, we are actually trying to calculate that limit in the middle. We are trying to calculate this limit right here. Look back up at the top there. That's where we left off, you see. We're trying to figure out what that equals. Okay? So, that's our goal. Now, what would this be? The limit as h goes to 0 of little m. Think about this for a minute. Okay, let's look back up at the pictures here. As h goes to 0, that means that I think I'm going to erase the pink lines out of our way here now. We don't need to look at those areas anymore, okay? So let's erase them so that we can see a little bit more what's in the picture. Okay, so now h is going to go to 0. So that means that this black line is going to slide over to this one. This black line will slide over to here. Okay? You have to remember now. Let's look at the third picture. What is little m? Lowercase m. It's the minimum value of f between x and x plus h. So, as x plus h slides over, okay, slides over to the left, at first, little m's not going to move, is it? But then, as that line continues to slide to the left, look, little m is going to be forced to change. Little m is the minimum. So as that line moves over, the minimum value is going to change. And eventually, what's going to happen? It's going to get smashed over and little m is going to be forced to line up exactly right there with that height. And what is that height? That height is f of x. Okay? So, the limit down at the bottom that I have circled in blue, that limit will actually be f of x. I should write it in gray. Okay, now, maybe you didn't quite get that. That's okay. We're going to do the same idea here, and you'll see the same thing happen again. Let's look at that limit that I circled in blue. The limit of capital M as h goes to 0. So let's look at the middle picture this time, okay? Capital M is the maximum height of our graph between x and x plus h. As h goes to 0, x plus h will slide over to the left. And that doesn't change the maximum value for a long time, right? The maximum is still right here. But watch what happens eventually. As this line slides over to the left, the space between x and x plus h shrinks. And eventually, there's no more space between x and x plus h. So the maximum value of f between x and x plus h ends up just being f of x. So this limit over here is also going to equal f of x. So that limit in the middle, let me just copy it down, is between f of x and f of x. By the squeeze theorem, that means the limit in the middle has to equal f of x. Do you remember that thing called the squeeze theorem? Okay. So let's scroll back up to where we had left off, up here. And now I can write down that this limit equals little f of x. And that's what we were trying to prove. Capital F of x prime, or I should say capital F prime of x equals little f of x. That's what I was trying to prove, because if you look back at the fundamental theorem of calculus, it says, then capital F is differentiable and its derivative equals little f. That's what we were trying to prove, and that's what we did prove. Okay? Now, that's only one step. We're going to take this another step further now. Okay, so I'm going to switch back to black. And in fact, maybe even what we'll do is let's shrink this stuff down. If you need to read any of this again, you can always rewind the video and watch it again. Okay? But I would like to move it out of our way so that we can just continue with what we were writing up above. Oh, sorry. Before we do that, one other thing. What if h was negative? Remember those pictures I drew depended upon h being positive. And when we had the inequalities down there, you can rewind and see again if you need to, but we had some inequalities that said this. We had that, and then we divided all three sides by h. And that's how we got this. The inequalities faced the same direction because h was positive. So I should just show you really quickly now. What if h was negative? Okay, would the math that we did still work? Well, it would still work out, because what would be different is, let's say here's x. Then x plus h would be to the left. If h is negative, then x plus h means you're taking some away from x. And so you would get that. Okay. And what we would have done, I don't think we need to go through the whole argument again. I just want to just convince you that the argument would still have worked. What we would have done is the area under the graph of f would have instead been the integral from x plus h to x. Okay? And when we divided that inequality by h, the directions of the inequality would have switched because we were dividing by a negative number then, if h is negative. Okay, and then I would do this. I would then multiply those inequalities by a -1, and we would get this. The inequalities switch sides, and the m's on the outside would be negative m's because of multiplying by -1. And then I would do this. Just one second here. Look at the middle. I would swap the x and the x plus h. You're allowed to do that. We talked about that. What does that do? That multiplies the integral times -1. So now that negative sign that was there, it was there, but now it would get canceled out because swapping these two multiplies by another -1. So we would be ending up with that. I forgot this negative sign over here at the end. Okay. And then the same idea. Hold on one second, I'm sorry. I said I forgot that negative sign, and that wasn't true. That negative sign disappeared because I multiplied everything by -1. My mistake was that I should have taken the negative sign off of the little m. There we go. Now it's correct. And you see now, this matches exactly what I had written when we went through the whole argument with h being positive. Same exact thing is written down. You do the limit as h goes to 0, and this part over here becomes f of x. This part here becomes f of x. And so therefore the limit in the middle becomes f of x. Okay, when you do the limit as h goes to 0. Okay, it's a little hard to follow these arguments sometimes because they're pretty abstract, but hopefully it makes some sense to you. Okay, so let's shrink this out of the way here, and let's go back to where we had originally left off our discussion that we were writing in black ink up at the top. Get all of this stuff out of our way. Okay, so let's just go back to this here. So we wrote that down at the beginning, and then we took some time in gray ink to prove that what is written on the screen right now is correct. Okay, now I want to add a little bit to this. Furthermore, the integral of little f from a to b will equal capital F of b minus capital F of a. And that's very important because that's what we use to calculate integrals. That's the formula that we use to calculate integrals so that we don't have to do the whole Riemann sum mess. Okay, so let me prove that last little sentence to you. This is actually quite easy. Okay. Okay, how are we going to prove that? So let's see be any number between a and b. Okay? Then I can take the integral of little f from a to b, and I can break that up into the integral of little f from a to c, and then add on to that the integral of little f from c to b. Okay, and one other thing, on that first integral there, I'm going to swap the limits of integration, and I'm going to write c on the bottom and a on the top. What does that do? That multiplies the integral times a -1, so I get a negative sign in front. Okay. Now, let's see if we can see up here. I want you to look back up at this right here. Would that change at all? This is a question I'm asking, a hypothetical question. Let me circle that letter A right there. What if I changed that letter? What if I changed that letter to a letter C instead? Would that affect any of the mathematics that we did? It wouldn't, would it? If you remember all the pictures I drew earlier, remember, I won't do the whole thing again, but remember, we were only looking from x to x plus h, remember? And I said A would be somewhere out here and B would be somewhere out here. But A and B didn't have anything to do with the proof, did they? So that letter down there, once again, this letter right here, being A, that did not affect any of the mathematics. If that had been a C instead, then the math would still have worked out the same. So why am I bringing that up? The reason I'm bringing that up is because look down here at what we have. Okay, and let's go back up and let's just suppose I replace that with a C right there. Then wouldn't this integral right here, then, wouldn't that just be capital F of B? And wouldn't this integral right here just be capital F of A? So look at what I'm left with there. And let's flip those and write it this way. How about that? That's what I was trying to prove, isn't it? So what have we accomplished here? What we have accomplished is this. Several lectures ago, maybe let's say 3 or 4 lectures ago, I showed you something called a indefinite integral, which just meant antiderivative, right? And then I showed you something called a definite integral. Let's write down an example again. Let's say something like this. Let's put this time 5x, no, let's not make it 5, let's make it 4x integrated from, let's say, 2 to 5. Okay. And what I told you was this. I said, how do you calculate something like that? I said, you find the antiderivative of 4x, which, what would that be? Wouldn't that be 2x squared? Right? And then I said, you write this vertical bar, you put a 5 there, and a 2 there. And I said, what you do is you calculate 2 times 5 squared minus 2 times 2 squared. I said that's how you calculate it, and so we would end up with 50 minus 8, so we would get 48 would be our answer, correct? So I told you, I said that's how you do a definite integral. You find the antiderivative, and then you plug in the 5, and then you subtract, and you plug in the 2. Okay? What we've done today is I just proved that formula for you. Here's the antiderivative. There's the 5, and there's the 2. So what we did today is we just saw the proof of why that is the correct way to do an integral, a definite integral. You find the antiderivative, you plug in the top limit of integration, and then you minus, and then you plug in the bottom limit of integration. Okay? And so that completes all of the explanations about integrals. And so what we're going to do for the rest of the time is we're just going to practice doing integrals for the rest of the lectures. Okay? So there's no more abstract stuff. I know the last few lectures have been very abstract. Okay? But now we're going to get back after this to more concrete things and just practicing routine computations.